Alright, lift off and the clock has started.
Hey, it's Ben here. When we put satellites and capsules and space stations up there into space, they stay up there, or at least until we tell them to come back down again. And that's because there's no gravity in space, right? You know, we just put them up there and then they float around. And that's a fairly easy assumption to make. I mean, you just have to look at astronauts floating around inside the International Space Station having a lot of fun. But if only it were that easy, frankly, because there is gravity in space, and there's gravity everywhere in the universe. Even very small things like these two pens. If I were to put them out where nothing else would affect them in the universe, they would just attract together due to gravity. They would fall towards each other. So why is it that our satellites don't fall down to Earth? Or more accurately, why don't they fall and hit the Earth? The answer to this is orbiting. Orbiting is that thing you've probably heard of where things will circle around the planet, but wouldn't that just make it harder than just having them in one spot? How does that stop them from falling and then hitting the Earth? Well, to answer this, we have to think about what would happen if we didn't put things into orbit, if we just launched them straight up. This is kind of like going out into your backyard, picking up a ball and throwing it straight into the air. It would go up and then fall right back down again, probably on top of your head, and that's not very good. So what would you be more likely to do? You'd throw it at an angle, right? And it would go up and then curve and come back down. How does this apply to orbiting? Well, we've got to zoom out and look at the whole planet and look at our tiny little rocket there, and it will launch up, and it launches to quite a high speed. But if we look at this, we're not launching super fast, and so we curve up and then come back down again. What happens if we increase the speed? Well, the same thing happens, except we travel further distance, right? But you might notice something important. Not only have we traveled further distance, we've traveled around the planet a bit more. So let's launch to an even higher speed now, really, really fast. We'll reach a magical speed called orbital velocity. This is when we go so fast that our curve turns into a circle, and it actually matches the curvature of the Earth. So we're actually using gravity to curve us around, so we're constantly falling but constantly missing the Earth. So let's think about this in chunks, right? We're falling a bit now, okay, but now the Earth is slightly, relative to us, a bit different. So we're going to fall and then miss, and then fall, and we're going so fast that we're going to miss, and then we fall, but again miss. So we're constantly falling, but we're constantly missing the Earth. That's why I said it was about not hitting the Earth. Okay, so this is how we're going to stay up there with gravity. But does it explain why our astronauts on the space station can float around? Well, yes, it does. But to understand this, we have to distinguish something. Gravity and apparent gravity. You see, here on Earth, we don't strictly feel gravity, we feel the effect of gravity. We feel being pushed into the Earth. We feel ourselves being squished. But on the International Space Station, for instance, they won't feel this. This is because the astronauts inside it are also falling towards the Earth, just like the space station around them. And because them and the space station are both falling towards the Earth, what happens is that there's no difference between them. You see, they won't get squished into the floor of the space station, and so they can just float around. I I hope this helped explain something to you. Or if you already knew a bit about it, hopefully it made it a little bit more easy to understand. As always, welcome to space.